Hello, this is module 3 of the SWAYAM RPIT course entitled as Low Energy Integrated Analog to Digital Converters with focus on SAR ADC. And in this module, we will review some of the techniques for switching of the DAC capacitors to save energy. Outline of this module is mainly divided into two parts. One is showing you the main structure of differential SAR ADC, and the second part reviewing some of the most efficient capacitive DAC switching techniques for saving energy in SAR ADC. So, what would be the main structure of a differential SAR ADC? So, in this slide, you see the main structure of the SAR ADC with focus on the DAC part. And as you see, we have different voltage levels and we have a fully differential architecture. For clarity, the voltage levels are shown on the right side. We have a common mode level, VCM, because we are talking about single supply system. And as you observe, comparator is a single supply comparator. So therefore, the analog input needs to have a common mode level. So this common mode level is shown with VCM. Now, interesting point is, in differential architectures, even though we have to spend almost double of the real estate on the chip, but the advantage is we get almost double of the possible swing in single-ended version. So here, for the single-ended switching, the voltage changes from V common mode minus V full scale by 4 and V common mode plus V full scale by 4. Therefore, the actual single-ended switching is V full scale by 2 full range. And when it gets converted to differential, it becomes V full scale. So here, what we mean from V full scale is the full scale range of the ADC for differential operation. So for example, if input is a sine wave which is shown in the lower part of the slide, we will have a situation like this. We have two inputs which are eventually of 180-degree phase difference, and therefore, when we take their difference, the actual amplitude of each one of them will get multiplied by 2. So therefore, we will get the double swing. And each one of them is swinging between V common mode minus V full scale by 4 and V common mode plus V full scale by 4. So having this in mind, now we can move on to operation. So as you observe here, we have two sets of capacitive bank. These capacitive banks are used for positive and negative half circuit of the charge redistribution tank. And the switching arrangement shown over here needs the following reference levels: V common mode minus V full scale by 4, V common mode plus V full scale by 4 for the positive side, and similar levels for the negative side, or half circuit, positive half circuit or and negative half circuit. The input voltages are V in P and V in N, positive and negative inputs, which are eventually differential components of the input. The actual input is not referred to the ground. The actual input is V in P minus V in N. And two sampling switches are shown at the input, which sample the input on the one plate of sampling capacitors, which are also playing the role of digital to analog conversion. And then we will have the comparator followed by the SAR logic. Output of the SAR logic not only is the final digital code, but also control signals at every cycle of the conversion. So therefore, this is an example of the fully differential architecture. Now we move on to switching schemes. Let's start with the traditional switching scheme. In the traditional switching technique, we start by sampling the inputs. In fact, sampling the inputs on one plate of capacitors almost is followed in all switching techniques. So let's see how much energy is consumed in these transitions. So for simplicity, a 3-bit ADC is shown here. So the initialization is performed by closing the sampling switches at the input and sampling them on one plate of capacitors. What about other plates? What are we going to store on the capacitors? Eventually, the same way we proceed with single-ended version, here also we assume at any site, either V in P or V in N, a well-defined DAC level. So here, for example, we are looking at a half of full scale at each site. Therefore, the V in P site is initialized in such a way that the MSB capacitor is connected to the negative supply, negative level, which is VCM minus V full scale by 4. When I say negative, it doesn't mean the absolute value is negative. Everything is positive. Negative in the sense that if you put VCM aside, you have minus V full scale by 4. So when I say negative, I mean minus V full scale by 4. So one terminal is connected to VCM minus V full scale by 4 of the MSB capacitor. And the other terminal and the similar corresponding terminal of other capacitors is connected to VCM plus V full scale by 4. Therefore, we have exactly division by 2 over here. For the negative input or V in N, of course, when we say negative input, it doesn't mean it is negative. It's just a terminology we define V in P, V in N. So it doesn't have anything to do with their sign. They are always of 180-degree phase difference with respect to each other if we put V common mode aside. So similarly, we will have the complementary arrangement for V in N. So therefore, the bottom plate of MSB capacitor, which is 4C here, is connected to VCM plus V full scale by 4, and the remaining corresponding terminals of the capacitors are connected to VCM minus V full scale by 4. So this is initialization. Eventually, we are initializing the voltage across capacitors in this way. But the first comparison is between V in P and V in N themselves. It doesn't have anything to do with the voltage stored on the capacitors. So when we open the switches, which naturally doesn't dissipate any energy by the reference levels, which is VCM plus V full scale by 4 and VCM minus V full scale by 4, we see the comparator is actually comparing V in P and V in N. If V in P is more than V in N, output of the comparator will be 1, and if V in P is less than V in N, output of the comparator will be 0. So now, when we move from this step to the next step, the decision and the switching depends on the decision. So let's assume, for example, the output of the comparator is 1. That means now we have done one round of the comparison or binary search. So it is V, which is V in P is more than V in N. So if that is the case, therefore, in this traditional switching, what we do is we try to reduce the effect of V in P and increase the effect of V in N. In other words, we try to reduce the range of the search by reducing effective voltage for V in P and increasing the effective voltage for V in N for the comparator. So that is the reason the next capacitor in the row, which is 2C capacitor, is connected to VCM minus V full scale by 4, and the other corresponding capacitor in the negative half circuit, which is 2C at the bottom side, is connected to VCM plus V full scale by 4. And the original connections with respect to MSB capacitors are not changed because output of the comparator is 1. Therefore, the initial assumption was correct. However, if the output of the comparator is 0, we have to perform effectively 4 switchings because the first part, which is related to MSB capacitors, have to be toggled. So, as you notice, green has become red. That means connection to VCM minus V full scale by 4 now has been replaced by connection to VCM plus V full scale by 4. Similarly for the negative half circuit. So now because the output is 0, that means V in P is less than V in N. So therefore the next capacitor in the row, which is the capacitor 2C, will be connected for the V in P side, will be connected to VCM minus V full scale by 4, and the other side will be connected to VCM plus V full scale by 4 to take the next decision. So this is the same direction of the initialization we consider. So now how much energy is dissipated? It's very interesting to notice. If the decision is 1, so we are eventually moving in the right direction. So that means the initial assumption of considering V in P is more than V in N was correct. Therefore, connection of the first MSB at capacitor, which is at the positive side to VCM minus V full scale by 4, was the correct. So therefore, we don't have too many switchings. In fact, only capacitors 2C are switched. And therefore, the energy which is drawn from the reference levels is CV full scale by 2 whole square. So this is for the decision 1, or when V in P is more than V in N. But if it is opposite case, we have effectively 4 switchings, or each side we have 2 switchings. So the energy consumed will be 5 times more because of this extra switchings. So decision making continues in the same way. For example, if we move in the right direction, output of the comparator still is 1 even in the second case, in the second step. So therefore, the third capacitor in row, which is capacitor C, will be connected to VCM minus V full scale by 4, and the corresponding capacitor will be connected to VCM plus V full scale by 4. Otherwise, we have to toggle the switching. And that's why, as you notice, again energy consumed for transition, if the decision is 0, is more as compared to the case decision is 1. And we have also 2 switchings at each side. So similarly for the other case, when the output of the comparator was 0, so we move to the next comparison, and then we have again division of energy consumption, and as you see again, when the output is 1, energy consumption is less as compared to the case when output is 0, because we should have always more switchings when output becomes 0. So here we will review a numerical example for better understanding. Let's assume V full scale is 2 volts and VCM minus V full scale by 4 is 0 volt, the minimum voltage with a single supply, and VCM plus V full scale by 4 is 1. And value of common mode voltage or VCM is 500 millivolt. So now let's assume input is 200 millivolt at the positive side, V in P, and V in N is 800 millivolt or 0.8 volt. And we are continuing with example of 3-bit ADC. So we start from step 1, which is shown by timestamp T. So inputs are sampled and the arrangement of the switching is exactly same as what we observed in the previous slide. So therefore, the top terminal of 4C capacitor at the positive half circuit will be connected to VCM minus V full scale by 4, and the opposite connection will be for the negative half circuit. Similarly, for other switches, we will connect to opposite level, which is VCM plus V full scale by 4 for the positive half circuit and vice versa. Now, the first decision has to be made. So, the first decision is made when Vxp is compared Vxn, which is same as V in P and V in N at this stage, because there is no charge transfer between capacitors ideally. So, the output of the comparator will be 0 because V in P is less than V in N. So, we are effectively in a case that the decision is opposite to our assumption. So, therefore, we will have a large number of switchings. So, in this slide, now you observe the switching which is happening at the positive side and at the negative side, similar to what we discussed before. And the corresponding diagram is shown on the left. In the corresponding timestamps of 2t, 3t, and 4t, we have transitions. The first timestamp is the sampling phase when we sample the inputs on the one plate of capacitors. So, as you see, the Vxp is less than Vxn. So, therefore, effectively, the DAC voltage levels move in such a way that, or change in such a way that, the effect for Vxp increases and the effect for Vxn reduces. In other words, we are reducing the range of the search area by proper switching according to the output of the comparator, which was 0. That means because Vxp was at the lower side, so now we are trying to increase that, and that's why Vxp in the next round increases to 450 millivolt and Vxn reduces to 550 millivolt. And this switching is performed by the switching you observe with respect to capacitors 4C and 2C. So 4C is connected to the VCM plus V full scale by 4, and the next bit is set at VCM minus V full scale by 4, next connection, which corresponds to the next bit. So now, when we move to the next switching, in this case, output of the comparator has to be checked again. Now here still Vxp is less than Vxn. Therefore, output of the comparator becomes 0. Therefore, bit V1 also is 0. So, therefore, in the next level, Vxp increases further and Vxn reduces further. And for this purpose, we should keep the switchings again toggled, and the way it is shown in this figure. And then finally, we will get V0 equal to 1 because now Vxp has increased with respect to Vxn. So, here in fact in this example is the example which is the worst case for energy consumption, because we will have the maximum number of switchings, because every time the decision which is made is opposite to the assumption, and that's why the energy consumption will be the worst case condition. So now how to improve the energy efficiency? To improve the energy efficiency, different techniques have been reported. We will have a review of a couple of these techniques from this slide onwards. So one technique tries to reduce the number of switchings by performing monotonic switching. In monotonic switching, there will be always switching at one of the half circuits or one of the half DACs, and this way energy consumption is reduced. How it is performed? Because it is monotonic, therefore both sides will be initialized at the same level. For example, here VCM plus V full scale by 4, And the first comparison will determine which side or which half circuit of the DAC has to switch. So for example here, when we open the switches at the input and the comparison is done, energy consumption is 0. So now, based on the output of the comparator, whether it is 1 or 0, the decision has to be made. Now, interesting point here is switching will be performed at one side. For example, if output is 1, that means we have to reduce the effective voltage at the V-in P side. Therefore, the MSB capacitor is connected to VCM minus V full scale by 4. That's it. No switching will be performed in the other side. If the output of the comparator is 0, then the switching will be performed in the opposite side, because now we have to reduce the effect of V-in N, or eventually reduction of the surge range by switching one side only. Now let's move on in this direction and see the energy consumption. Now here, because we are performing only one switching, energy consumption is simply C V full scale by 2 whole square, which is less than the traditional case. If we continue in the same path, we have again two conditions for the comparison. If it is 1, output of the comparator is 1, so that means our assumption has been in opposite direction. So therefore, we have to now reduce the effect of VXP, which is done by connecting only VXP to VCM minus V full scale by 4, and the negative half circuit will not have any switching. Similarly, if output is 0, that means we have to further continue with reducing the effect of VXN, which is done by connecting the second capacitance in the row, which is capacitor C, to VCM minus V full scale by 4. And therefore, as you notice, the energy consumption is less than CV full scale by 2 whole square. For one case is 75% of it, and in the other case is 25%. So energy consumption has reduced. Another capacitance switching technique is called merged capacitor switching, MCS technique. So reference for these techniques are provided at the bottom of the slides, so interested audience may go through the corresponding paper. So this technique eventually brings one more reference level to the picture, which is VCM itself. Common mode level also is available and should be available. And in fact, initialization is performed with respect to the common mode level, not actual reference levels for the DAC. So what is the advantage over here? So the advantage over here is because initialization is performed at VCM, so the variation of the voltages is not all the way from minus V full scale by 4 to plus V full scale by 4 or vice versa. It is actually from VCM to these levels, and therefore energy consumption reduces. So first, all capacitors, just like the monotonic switching, are connected to VCM, but VCM, not reference levels for the DAC. And the inputs are connected to the inputs of the comparator for the comparison purpose. Then, same as before, in this case, no energy will be consumed because for the first comparison, only switches are opened at the input. So no energy is dissipated or drawn from the input reference levels. So now again decision is made, V in P will be compared with V in N. If V in P is more than V in N, that means we have to reduce the voltage at the V in P side and increase at the V in N side. So that's why we have the connection to the positive supply for the V in N side and connection to the negative supply at the V in P side. So we have two connections, but voltage levels are moving from VCM to VCM minus V full scale by 4 and VCM plus V full scale by 4. If the decision by the comparator is 0, in other words, comparator says that V in N is less than V in P, so in that case, the switching will be opposite to the switching which happened for the case output was 1. And we follow this path for the example of the expression for the consumed energy. Now, because switching levels are changed from initial value of VCM minus V full scale by 4 to VCM or VCM plus V full scale by 4 to VCM. So, here you see there is a factor of 1/2. Fraction of CV full scale by 2 whole square is consumed, and therefore energy is saved. Now, similarly, if we move on to the next level of comparison, depending on the output of the comparator. So, suppose output of the comparator is 1. So, we will have the next switching. This switching also will be in a completely symmetric case with opposite signs in the two sides. So, we have double switching but with a reduced swing. And therefore, as you can see, the fraction of CV full scale is by 2 whole square is consumed in both cases. Either output of the comparator is 1 or output of the comparator is 0. In both cases, fraction of CV full scale by 2 whole square is consumed. In fact, a very small fraction, 1/8 and 5/8. So, energy here is saved even more. So, to have a better visualization of the way switching is happening and the area of search is narrowed down in these two cases, I show you two diagrams of merged capacitor switching and monotonic switching. So, as we discussed, in the merged capacitor switching, we have still double switching. Both sides are switching. But because of the reduced swing for every transition, the energy consumption reduces. So, on the left side, you see an example for a 4-bit ADC. And when V in P is more than V in N, and VCM is shown in this figure. So, the initial difference between V in P and V in N is shown by delta V1. Because V in P is more than V in N, the corresponding levels will reduce for the voltage which is more. So, because V in P is more, so the corresponding level will reduce for V in P, and the corresponding level for V in N will increase. And therefore, the region of search is reduced to delta V2. In the next step, because still V in P is more than V in N, the direction of reduction and increase will be same as before. So, still the level corresponding to V in P will reduce, and the level corresponding to V in N will increase. So, now we face the situation when the corresponding level to V in N is more than V in P. Therefore, the opposite direction of increase and decrease will happen. And therefore, only in this case, which is bit 3, we will have bit 0. Other bits remain 1. So, therefore, the corresponding code is 1101. Now, if you go with monotonic switching, which is for the same inputs, so initial difference delta V1 is same, but now the switching happens in such a way that only one of the inputs has the transition, but this transition has a higher swing or higher difference between the new value and the previous value as compared to merged capacitive switching. And that's why even though one side is switching, but the energy which is consumed for the switching is more as compared to merged capacitor switching. The next technique is VCM-based monotonic switching technique. This technique also takes advantage of reduced capacitors even further. You may have noticed in monotonic switching, we didn't have capacitor for C for 3-bit ADC. Because of the monotonic switching, which is eventually switching in one side, we didn't need MSB capacitor. So here, the technique takes advantage of even voltage switching, and therefore even we need less number of capacitors. So now capacitor 2C is also removed for a 3-bit ADC. So this technique not only reduces the energy but also reduces the area. So what it needs is to have VCM available, and switching also is performed with respect to the voltage levels. The first phase is the initialization phase, which is shown here. The initialization is performed by connecting one plate of all capacitors of the DAC to VCM, which is the common mode level, and sampling the V in P and V in N on one plate of capacitor, same as other techniques. So therefore, the first stage is same as before, the first step or the first sampling phase, and then comparator performs the comparison of V in P and V in N, same as other techniques. Now, depending on the decision of the comparator, if it is 1, that means V in P is more than V in N, we move to the next switching. And if it is 0, we move again to the next switching. Now, here is a very interesting situation. Let's start from 0 and see that how the energy is consumed. If the output of the comparator is 0, that means V in P is less than V in N, or V in N is more than V in P. Therefore, V in P side has to increase. Eventually, the positive terminal of the comparator should have increased voltage. So now, for this purpose, switching is performed at the voltage level only. So therefore, here we are not generating any difference between the voltages of the capacitors at one terminal with respect to other capacitors in a half circuit. All of them are switched. So all capacitors of the C in the positive half circuit of the DAC get their top plate connected or switched from VCM to VCM plus V full scale by 4. In this way, we will have the new voltage level. However, we will not have any energy consumed. Because switching has happened for all capacitors, therefore, there is no charge distribution. And the consumed switching energy is 0. In other words, no energy is drawn from the voltage references. So, therefore, it's very energy efficient and it's very relatively area efficient as well compared to other techniques we have reviewed till now. So now we move on to the next level. So next cycle of conversion starts again based on the decision of comparator at this stage. If the output of the comparator is 1, that means positive terminal was more than the negative terminal. If the output of comparator is 0, that's the opposite situation. Now, depending on that, the situation will define the next switching. Now, what is the next switching? In this case, suppose output is 1. So, if output of the comparator is 1, now that means we have to reduce the potential at the positive terminal of the comparator. So, that's why here this reduction is performed by switching one of the capacitors now, and therefore we can move in the binary search direction by providing the half of eventually full scale range with respect to the previous cycle. So therefore the range is, the dynamic range now is divided by 2 for the search by just switching one capacitor, and this switching is switching from V full scale plus Vref by 4, bring it back to the VCM level or common mode level. If the output of the comparator is 0, that means V in N is more than V in P. Eventually, that means the negative terminal is more than positive terminal. So what I mean from V in P, V in N, sometimes I use them instead of positive and negative terminal. I mean negative and positive terminals of the comparator. So now in this case, negative terminal is more than positive terminal. So that means we have to reduce the negative half circuit, corresponding voltage with the negative half circuit. So now to do that, it can be done still with one capacitor switching to move to the next eventually range, which is half of the current range. And also because we have already VCM available, we can simply switch it to VCM minus V full scale by 4 to reduce the negative terminal voltage at the negative terminal of the comparator. Now having that, energy consumption extremely reduces. In fact, here in both switching cases, it's only a fraction 1/8 of CV full scale by 2 whole square, which is lowest among all these 4 techniques that we reviewed today. Now to get a better idea about the difference between the two techniques of monotonic switching and VCM based monotonic switching, this diagram is shown here. So let's assume V in P is more than V in N and the common mode level is shown for both switching techniques. So first part is comparison of V in P and V in N. So after that comparison is performed and the output is 1, because the V in P is more than V in N, therefore the corresponding half circuit DAC will operate and the corresponding level at the positive terminal of comparator will reduce. So in the next cycle of conversion, because still the V in P is more than V in N, V in P side or the positive terminal of the comparator is still more than the negative terminal. Therefore, next bit will be 1 and we will have one more cycle for the reduction of the voltage. So the positive terminal of the comparator will have one more reduction by monotonic switching. Now in the next cycle of conversion, because now the negative terminal side has increased is more as compared to the positive terminal of the comparator. So therefore in the next cycle of conversion, the V in N side will reduce and the corresponding bit will be 0. So this is for a 4-bit DAC and the corresponding 4-bit ADC for the monotonic switching. Now if we have the same input levels, same common mode level for the VCM based monotonic switching, you observe that the swing is less, but still it is monotonic. So V in P is more than V in N, so V in N increases, V in N side increases, which is the negative terminal of the comparator. And then V in P side reduces, which is the positive terminal of the comparator. And then we will have another reduction which is monotonic only for V in N. So therefore, we will have always monotonic switching, but the amount of switching is less and number of capacitors has reduced, and we have also smaller values of capacitors. In fact, capacitor 2C, which was available for and which is necessary 2C and 4C for 3-bit and 4-bit conversion, they will reduce for the VCM based monotonic switching. So to have a comparison of the energy efficiency, a table is shown over here, and we have here 4 techniques which are reviewed in this course. One is traditional technique, which is used as a reference, monotonic switching, merge capacitor switching, and VCM-based monotonic switching. So consume energy, switching energy is shown as a factor of CV full scale by 2 whole square, means that this is used as a quantized level. So how much with respect to this? Eventually multiple of this value for a 10-bit ADC. And the reference papers are shown at the bottom of this slide. So traditional surprisingly consumes a lot of energy, more than 800 times of this unit, while monotonic switching reduces the same consumption to around 250, so 256 times. But merged capacitor switching and VCM-based monotonic switching reduce it below 100. And in fact, VCM-based monotonic switching reduces it to simply 32 times of the unit, which is 96% reduction. What about capacitive DAC? So in capacitive DAC, for an n-bit ADC, we need to have 2 to the power n plus 1 C. If we go with monotonic, so number of capacitors reduced by a factor 2. Merged capacitor switching is the same, 2 to the power nc. And then in VCM-based monotonic, because we eventually don't have the MSB capacitor which is used in other switching techniques, therefore the number of capacitors are reduced to 2 to the power n minus 1 C. The only difference is we should have the common mode level available for merged capacitor switching and VCM-based monotonic switching. But if this VCM is available already, so we don't have any overhead. For example, if you have a case when the analog and analog part, signal conditioning, instrumentation, interfacing, as well as ADC are in one place, so therefore naturally VCM is available, and therefore there is no overhead by having one extra common mode. So conclusion is we have reviewed 4 differential architectures of SOR ADC with respect to energy consumption, and this energy consumption is mainly because of the capacitive DAC switching, and therefore it's important to take care of the energy consumption. And of course, we know that the differential configurations add to the area because almost number of elements is doubled. Therefore, if we use systems or switching techniques which help us to reduce number of capacitors, we save both energy and area, and that's why VCM-based monotonic switching scheme seems to be the best with respect to having both area and energy reduced at the expense of adding one reference level, which is eventually common mode level, and if it is already available in the system, that is not an overhead. So with this conclusion, we reach to the end of today's module. Wish you all the best.